Physicists at Chalmers University of Technology in Sweden, together with colleagues in Russia and Poland, have managed to achieve ultra-strong coupling between light and matter at room temperature. The discovery is of importance for fundamental research and might pave the way for advances within, for example, light sources, nanomachinery, and quantum technology. A set of two coupled oscillators is one of the most fundamental and abundant systems in physics. It is a very general toy model that describes a plethora of systems ranging from guitar strings, acoustic resonators, and the physics of children's swings, to molecules and chemical reactions, from gravitationally bound systems to quantum cavity electrodynamics. The degree of coupling between the two oscillators is an important parameter that mostly determines the behavior of the coupled system. However, the question is rarely asked about the upper limit by which two pendula can couple to each other, and what consequences such coupling can have. The newly presented results, published in Nature Communications, offer a glimpse into the domain of the so-called ultrastrong coupling, wherein the coupling strength becomes comparable to the resonant frequency of the oscillators. The coupling in this work is realized through interaction between light and electrons in a tiny system consisting of two gold mirrors separated by a small distance and plasmonic gold nanorods. On a surface that is 100 times smaller than the end of a human hair, the researchers have shown that it is possible to create controllable ultrastrong interaction between light and matter at ambient conditions, that is, at room temperature and atmospheric pressure. We are not the first ones to realize ultrastrong coupling. But generally, strong magnetic fields, high vacuum and extremely low temperatures are required to achieve such a degree of coupling. When you can perform it in an ordinary lab, it enables more researchers to work in this field, and it provides valuable knowledge in the borderland between nanotechnology and quantum optics, says Denis Baranov, a researcher at Chalmers University of Technology and the first author of the scientific. To understand the system the authors have realized, one can imagine a resonator, in this case represented by two gold mirrors separated by a few hundred nanometers, as a single tone in music. The nanorods fabricated between the mirrors affect how light moves between the mirrors and change their resonance frequency. Instead of just sounding like a single tone, in the coupled system the tone splits into two, a lower pitch, and a higher pitch. The energy separation between the two new pitches represents the strength of interaction. Specifically, in the ultrastrong coupling case, the strength of interaction is so large that it becomes comparable to the frequency of the original resonator. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.